Hello, welcome to day 31. So today we're going to talk about wave behavior, and we're also going to start talking about sound. So let's go ahead and get started because there's a lot to cover. Okay, so 14.3 talks about wave behavior. Wave boundaries have to do with water, has to do with depth. Sound has to do with temperature. Spring has to do with tension and mass. Incident wave is a pulse that strikes boundaries. You have reflected waves, which are turning waves. And then you have hide and rigid boundaries. So when we have a superposition wave, we have something that is going through, and it's going to something that is attached. So if it's going up on the way in, say it's attached to the wall, on the way back down, the wave is going to be on the other side or dipping. Superposition waves, and principle of superposition displacement of a medium caused by two or more waves in displacement caused by individual waves. So we have what's called interference. Interference is like you have an incident wave of 3 centimeters, a reflective wave of 1 centimeter. That's going to be equal to 2 centimeters. That's going to be the difference between those two. Destructive is where two waves come from two opposite directions. You have a high and a low, and they change places as they go across. A constructive wave is where two waves coming from two different directions, but they add up together. So I did not draw the picture, but there was a really good picture in the textbook that had to do with these two right here. And you could draw these if you want to, if you still don't understand the concept. Okay? We have what's called a node, which is where the displacement is 0. And then you have what's called an antinode, and that's A, and that's where the displacement is the largest. The next thing it talks about is a standing wave. A standing wave we did a little bit about at the very beginning of the year when we were using the harmonic wave maker, where we had it where it was doing the wave and it looked like we were trying to make one. Remember that? That is where they come together and they look like that this wave is standing still. When you're talking about waves in 2 dimensions, you're talking about rays and wavefronts. A wavefront is a line that represents the crest of the wave in 2 dimensions. A ray is a line drawn at the right angle of the wavefront. You have what's called reflection in 2 dimensions. And when we're talking about reflection in 2 dimensions, you have this where you have an incident wave, a normal, and then you have a reflective wave. A normal is oriented of a barrier line in between the two of them. The law of reflection, angle of incident is equal to the angle of refraction. Refraction is a change in direction of the wave at the boundary between two different medians. And that there is pretty much the rest of the sum of chapter 14. If you look on page 401, they have some really good study guide sections that you might want to make sure that you have these bullet points on in your ISM book. And so then now we are going to go to sound. So, sound. Sound waves are pressure oscillating that is transmitted through matter, and most sound waves transfer through the air. We as humans, we actually have at our ears where it goes from. It goes into the auditory canal, then it goes to the eardrum, and then the ambule, the piston, and the cochlea, and then it goes into the auditory nerves. So when we're talking about pitch, is the highness or the lowness of a sound. So they have sound levels have a wide range, and then they gave us a decibel sound or dB, and that's the intensity of sound. So if we had 10 dBs, that is barely audible. That means some people can barely hear it. If you have 30, that has to do with a whisper. 1 meter away. For a 50, that is a casual conversation. For a 70 is if you're in heavy traffic. 80 is your alarm clock. 100 is a siren. 110 decibel is a rock concert. And 140 decimal is a jet engine. Remember, there is a threshold of pain of what will hurt if the noise is louder than a certain thing that would cause you to stop. Okay? So then we have what's called the Doppler effect. The Doppler effect has to do with this equation, which is the frequency perceived by the detector is equal to the velocity of the detector relative to the velocity of the wave divided by the velocity of the source related to the velocity of the wave multiplied by the wave frequency. So, when I think of Doppler effect, I think of a siren or a police officer or an ambulance, and how when they're behind you, they sound so loud. But then once they pass you and they're in front of you, you barely can hear their siren. That's what I remember for Doppler effect. And then on page 415, there were also some equations here that you could have. I just did not write them down for sake of time. And then it talked about the example problem. And this says a guitar played a sound C with above a major C while traveling in a convertible at 24.6 meters per second. If the car is coming toward you with a frequency would you hear according to 20 degrees Celsius. So here we are. We have our velocity. We have everything that they gave us. And it's asking us to find it. To be able to find FD, we're going to take our FS, and then we're going to do 1 over 1 times 2.46 over 343, which is 564 hertz. And the only thing I did is I did the first two problems on the practice. So the first one says repeat example problem 1. For the car moving away from you, what is the frequency that you hear? So, since it's moving away from you, instead of having it at a positive 24.6, now I have a negative 24.6. So then going away from us is 488 hertz compared to 564. And then number 2, if you are in an automobile, like in 1, traveling sound from the pole mounted on a warning siren. If the siren's frequency is 365 hertz, what is the frequency that you hear? Use 343 meters per second for the speed of sound. So I'm taking the 365 hertz, and I'm timesing that by 343 plus 25 divided by 343, which I get 392. And then the last part with the application is going to talk about a bat and how a bat uses sonar. So what it does is a bat produces a loud noise, and that noise travels to where the bug is, and then when it hits the bug, it travels waves back to the bat where the bat can figure out exactly where it is. So that's, I think, is super awesome. And so then starting tomorrow, of course, what we're going to do is we're going to finish this section, and then that is it. So if you don't know, tomorrow is your last day for new assignments. And so after that, I think on Monday of next week, I'm going to go ahead and send out everybody a progress report. You have until next Thursday to do any makeup work. And then after that, I'll submit your grades on Friday. I hope you have a blessed day, and I miss you, and I hope you're having a great time.